out. Okay, recording to the cloud, recording with the little camera. Okay. Okay, starting the timer. Technology. Right, so we have questions. For assignment 2, the Brightspace due date is for the... What? Oh, that's a mistake. Oh, they've got some horn going. Okay, I can deal with this afterwards. Okay, the deadline for assignment 2 is Friday. Yeah, I probably got that messed up. It is like the coming Friday at the end of this week, because last Friday, because we need to have lots and lots of assignments in order to drop 2 of them. Right. So I will email Sarah. Okay. So today we're going to talk about bounds. So asymptotic notation, the master theorem, upper and lower bounds, and the master theorem. So this this is not sort of what I consider the most exciting stuff. Well, except the upper and lower bound stuff. Now that I've managed to sort of stuff that into this lecture, that I consider exciting. Okay. So first, you've probably all heard about the big O notation, right? I mean, you probably all use big O notation. Okay, I will email Sarah. Okay, for future reference, yes. If you have questions about something, email Sarah. I might be able to help you. You probably will be able to help you. Okay. So big O notation. People have seen, yes. People are saying yes. They've seen big O notation. Big O notation. Today, I'm going to try to teach you what it actually means and how you should actually use it. But that's like teaching you exactly the proper ways to use it. Well, I'm not going to, for example, I'm not going to get into how do you use it with 2 variables, because that's more complicated than you'll probably ever need to know. And actually, even the stuff I'm going to show you today, you don't really need to know exactly. I mean, in this class, yes, because if you don't learn it, I'll fail you. But once you get out into the real world, you're going to hear people saying things like, this takes at least O of whatever. And with luck, the stuff I'm going to teach you today, that's going to drive you nuts. Because it drives me nuts. It's like when people say, when people, you know how people say, she gave a cookie to Bob and I, and it should be Bob and me. Is it or say like Bob and me went to the, it's like, okay, like people, yeah, I could care less. Is that kind of stuff. Like when people, when they put apostrophes where they shouldn't put apostrophes, like there's a cartoon that says, if you really hate somebody, teach them to spot bad kerning. Kerning is the spacing between letters. Yes, that's an apostrophe. So I'm going to take that as an example, not as a message to me. Okay, so because there are things you should not say with big O. People tend to use big O for everything. They mean big omega and they say big O. And you should know what they mean. So I will do that. It's very hard. It's like using the subjunctive and stuff like that. Everybody makes mistakes. Okay. Big O means at most about. Big omega means at least about. Big theta means about. So we have, one of these days, I'm actually going to open this new pack of markers. So we have, yeah, maybe I'm going to be opening the new pack of markers. Oh no, there's this other pen. Okay, that's the very old blue pen. So big O of f of n means about f of n. Sorry. At most about f of n. Big omega of f of n at least about f of n. Big theta f of n about f of n. And then you have these little o and little omega. And those, they sort of mean, little o means sort of less than about. That's a bit harder to say it informally. Okay, so in the lecture notes, which I just uploaded, I started out by talking about my friend Simon, who is, he's a computer scientist, actually Simon, because he's German, and he's a runner. So he runs really long distances very fast, not quite as fast as Turing. But let's suppose that he runs, the time he takes to run distance n is, I said, suppose Simon normally takes time n to the, what did I say, 7/8? 7/4? You run distance. But Simon, he runs different speeds depending on whether he's had a coffee, or if he's got his favorite shoes on, or if he's tired, or whatever. So about this, time some constant. And we don't want to worry about these constants because, like, who wants to keep track of whether Simon's had a coffee this morning? So suppose I run normally so I take time n to the, no, wait, this was, Simon is 3/2, I think, and I'm 7/4. Okay, but maybe Simon gives me a head start, and maybe I have my favorite shoes on and he doesn't. So there's, this is some constant times this and some constant times this, and maybe I get, this is, he's going to give me a head start, so he's going to take n to the 3/2, c times n to the 3/2 plus 10. But you see that ultimately, if we run far enough, if we run for long enough, Simon's going to pass me, and then after that, maybe every so often he stops to tie his shoes or something, and I manage to catch up a little bit, but the functions are going to go, there's me, my distance, or let's say that this is, what do we want? We want time. No, we want time as the dependent variable in this. And this is the distance we run. And so I'm going to go like that. And Simon, Simon maybe starts out, he gives me a head start, and he's going to cross over, and then, so there's some wobbling around. We're going to cross, and ultimately Simon is faster than me. So my time is going to be, in the long run, Simon is faster. So you can see that regardless of whether or not he's had a coffee or whatever, Simon is faster. And so we want to be able to talk about ignoring things like head starts and shoes and coffees. And this is important in computer science because we don't want to care about, if we're talking about an algorithm, we don't want to talk about, yeah, that's, wait, but Simon is running, yeah, Simon is running at the 3/2, and I'm running, so I take more time to run, this is the time that I take to run distance n. Sorry, yeah, I originally was writing it one way. Maybe I've messed it up in the course, in the lecture notes. But the idea is, because programs, we usually talk about time. We talk about the time it takes to process an input of size n. We don't talk about the time is fixed, how much of the input can we process. So that's why I flip these around. So yeah, the distance here is n, and the time is some function of n. So yeah, okay, don't need to run. So okay, we want to be able to say things like, in the long run, Simon is faster. And we don't care about constants, because maybe I have another friend who's about as fast as me. And when you say about as fast, you want to mean like, yeah, okay, so depending on the day, depending on which shoes we're running, maybe one of us didn't have breakfast, but you see what I mean, about as fast and in the long run for sufficiently long distances, for sufficiently large n. Okay, so so first, oh, this is way down here. I want to look at the notes just to make sure I'm not forgetting anything. Yeah. Oh, I can't believe I wrote all this stuff. I put all that cool stuff in about Turing. All right. So one way we can say this is that if my time is, so Simon's time is f of n, or yeah. So Simon's time is f of n, and my time is g of n. So one way we can say this when we're saying for sufficiently large n, we can say limit as n goes to infinity of f of n over g of n is 0. Okay? For sufficiently large n, the time it takes Simon to run a certain distance, it's going to be a negligible fraction of the time it's going to take me to run the same distance. So this is assuming that, well, okay, I mean, if it's a sufficiently long distance, then it will actually be exactly 0, because I will probably collapse before I finish. So it will take me infinite time. So what we actually, to say this, computer scientists, we don't do this limit stuff. We just say f of n, this is little o of g of n. Okay? Or equivalently, you might say g of n is in little omega that looks like a W of f of n. So this isn't at most about, this is actually, you know, a lot smaller than, and this is a lot bigger than, but for sufficiently large n. So O comes from the phrase in English, on the order of. That's a little bit misleading because we say, for example, n, oh, and now I've gone and done this thing where I went and drew equals. And I actually wanted to draw set element. Okay, so n is an element of O of n squared. You've probably seen somebody write something like this. Okay, this is little omega. It looks like a cursive W. Would normally be the third notation. Third notation, not sure. Okay, so this doesn't mean, if you say, in English, if you say on the order of, you'd be wanting to say like, oh, Travis runs on the order of the same speed as Simon. Well, it's true that Travis's speed is less than Simon's asymptotically, but it's not, you know, roughly the same. So on the order of it usually feels like about the same. Like, oh, how long will this take, like on the order of 100 days? And if it then takes 2 days, you'd be like, well, on the order of, it's like order of magnitude, you know, or the same order of magnitude. And if it took 2 days, you'd be like, yeah, well, it was big O. It's not gonna work. So the origins of why this is big O are a bit misleading. Oh yeah, okay, please. What is little omega? We're going to get to that. Okay, so I have to keep switching back and forth because normally I practice before the class. I know it doesn't seem like that, but I actually do. I read over the notes, but I had a meeting this morning. Okay, so I was saying the thing we should get straight about big O and big omega and theta and well, you just saw me, I drew equal signs here. I shouldn't have done that. People do, but then people put apostrophes in bizarre places. These things are sets, okay? They are not values. Well, that could be a value, but okay, they are sets of functions. So what is big O? Well, big O of f of n, or let's say g of n, which is I think what I did in the course in the lecture notes. Big O of g of n is a set of functions. Big O of g of n. It's the set of functions h of n, such that h of n is at most about g of n. But at most about, in this case, has a very specific meaning. Now, if people have done, I'll switch back to the chat. So switching back to the chat, people have done epsilon delta ball proofs in calculus, right? Where you say, for every epsilon, there is a delta such that within a ball of radius delta of this point, this is when you do limits, right? Anybody? If you're within a ball of delta, okay, but somebody said yes. So some people have seen this. So I feel like this is something similar, right? So there exists an n0. So this is like saying for every, in epsilon delta ball process, like for every, excuse me, t. for every epsilon, there exists a delta. It's a bit backwards. But actually, it's closer when we get to the definition of little o, which makes sense because I just showed you that little o it can be defined in terms of limit. So there exists an n0 and a constant c greater than 0, such that for all n greater than or equal to n0. So this backwards e means there exists. Or in this case, there are two things, so there exist. This upside down a, okay, so let's make it bigger. H of n, H, not n of n. There exists an n0 and c greater than 0, such that for all n greater than or equal to n0. So, have people seen this in logic? Okay, maybe I need to move this closer. Discrete. I'm not sure how much closer I can move it. Because if I move it too close, you can't see the whole board. Okay. There exists an n such that for all n greater than or equal to n0, h of n is less than or equal to, I forget if this is, so I forget if it's usually a greater than or equal or just a greater than, but it doesn't matter because you can always choose your n0 plus a little bit. And this, I forget if it's a less than or less than or equal, but if you want it to be a less than, just choose your c a little bit smaller. Okay. C times J. Okay, so it's saying that for sufficiently large values of n, so there exists an n0 such that once you get past that n0, then for all of these, h of n is less than some constant times c of n. So maybe h of n is actually bigger, but it's at most going to be, for sufficiently large n, it's at most a constant factor bigger, right? You're like, well, it's not less than g of n, but it's always less than 5g of n once n is bigger than 100. Okay, so this is saying for sufficiently large n, and this is saying this is the at most about. This is a dot. This is a period, not. It's just when people write the exists for all, they terminate the quantifiers with a period. I forget if they terminate every quantifier with a period. Somebody asked, is that a multiplication sign after n greater than or equal to n0? Okay. Oh, and I was saying that the reason we want to say that the reason for running, you want to be able to say Simon, Travis is slower than Simon for sufficiently large distances, plus or minus up to constant factors. Well, actually, Simon is just much faster. We want to talk about this because if you change your computer, you add more RAM, the thing gets a bit faster. You use a different programming language, the thing gets a bit faster or slower. You hire a slightly better programmer, maybe the implementation gets a bit faster. You can do all of these things and it changes stuff by constant factors. And we don't want to talk about that when we're comparing algorithms. We also don't want to talk about like insertion sort is faster than merge sort when you're really dealing with small instances. We don't care about that. So we want to be talking about like, okay, ignoring constant factors that change based on your computer and ignoring small instances, we're saying that O of g of n is the set of functions h of n such that there exist n0 and c greater than 0 such that for all n greater than or equal to n0, h of n is less than or equal to c times g of n. So for sufficiently large n, h of n is at most a constant factor times g of n. Okay? Okay, just starting the high res camera again. Okay, so what does it mean exactly? It means at most about. H of n is at most about g of n for sufficiently large values of n. So for small values of n, h of n could be bigger, much bigger. Well, I mean, but quite a lot bigger. But then for sufficiently large n, it's not that much bigger. It's not more than a constant times bigger. So it could be like 5 times bigger. Then, let's not even talk about O, little o. So also, somebody just wrote little o. This is a big O, okay? And that changes. A big O and a little o are different. Okay, so that's most about. And this is the one people use all the time. And I need to restart the timer. Otherwise, we don't get a high resolution reset start. Good. So let's do, but you see, it's a set of functions. So when I say something like n is in big O of n squared, big O of n squared, big O of n squared is the set of functions h of n such that, so some people write colons, some people write a bar, such that there exists n0, c greater than 0, such that for all n greater than or equal to n0, h of n is less than or equal to c times n squared. Okay, is this true? So is n in O of n is 53 times n in big O of n squared? Well, is there an n0 and a c such that for all n greater than or equal to n0, so yes, let's say, so for n0 equals 60, c equals 32. Do we have, this is h, do we have 53 times n is less than or equal to 32 times n squared for n greater than or equal to 60? Yeah, I think so. Just a second. 60, yeah, this is true. Good, so we can choose n squared. So for all n greater than or equal to 60, this is true. Therefore, this is true. I hope this is true. Maybe I could have just chosen this to be like 600 to be sure. But okay, so that's what it means. So 53n is at most about n squared. Okay, what about big omega? Big omega g of n equals, Well, this is at least about. This is the set of functions h of n such that there exists n0, c greater than 0, such that for all n greater than or equal to n0, h of n, you just turn the inequality sign around. Right? Is c times g of n. Now, some people might move the c over, but that's fine. You just, like, we're choosing a positive constant, so you can just take the inverse. So it doesn't matter which side you write to c. So this just, okay, exactly the same thing. There exists an for sufficiently large n, h of n isn't too much small. And notice that c doesn't have to be an integer. H of n isn't too much smaller than g of n. So it's at least about. Is that e equals 30? C, that was a c equals 32. Somebody asked if it was an e equals 32 or c equals 32. Yeah, it's this c. So just to show the two functions that some function is in big omega of another function, if you want to do it like really thoroughly, you show that you can choose an n0 and a c such that this holds. Okay, so for example, I want to say that n squared is in big omega 53n. And notice that we don't actually, usually you don't write a constant in here, a constant coefficient, because it just gets eaten by this c. So constants disappear, lower order terms disappear. This is very handy. Why? Well, does there exist? Yes, that we just showed. There is 60, and c is 32, and then n squared is. Oh no, actually that didn't quite work. Okay, now I'm going to choose. Now I'm going to choose n0 equals 60. But now I want to make everything, because I didn't flip the side of c, I'm going to choose c equals 1 over 32. Okay, could it be contained in? Why does n squared equal big omega? Because n squared for sufficiently large n is at least about 53n. N cubed is at least. It's actually much bigger. N is in big omega of 53n. Square root n is not in big omega of 53n. Even 1,000 square root n is not in. And I went and wrote the equal sign again. It's a set. It's not a thing. Okay. So for example, you have 1,000 square root n is not in big omega of n. For small values of n, 1,000 square root n is going to be bigger than n. But for sufficiently large values of n, it's not. Okay. So then we get into okay, so the thing is, I'm going to zip through this, because if you want practice with big O, big omega, big theta, blah, 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 you can get it other places. Okay, I'm supposed to teach it to you, but I'm actually supposed to teach you a lot in this semester. And I'm probably not good at this kind of stuff as the videos you can get from like Khan Academy. You can just find stuff on YouTube. This asymptotic notation is in all of the introductory algorithms courses. And so there are things I want to emphasize. Is it generally true that if it is in if f is in big O of g, then g is in omega f. Yes, yes, this is true. So then you have theta of n, and I said that was about, and that's just the intersection. Oh, okay, let's say I want this to be g of n. That's the intersection of O of g of n cap intersection with omega g of n. Okay, so if some function is in theta g of n, it means it's at most about g of n and it's at least about g of n, so it's about g of n. Okay, and now we get to that. So little o, which is what we saw when we were talking about Simon's time is little o of my time. I'm probably getting some of these backwards, but like watch the Khan Academy stuff. I want to talk about, there's something people say that, again, drives me nuts, like apostrophes or something. And that I really want to address, because that's, I think, more important than it's important to get this stuff down, but you can get this, you can practice this offline. It's more important that I tell you something that people seem to get confused about. Okay. So we want to say not just that Travis's time will be at least about Simon's time. We actually want to say the time Travis takes to run distance n is going to be a lot more than for a sufficiently large n, and regardless of a constant head starts and shoes and whatever, Travis is slower, not at most as fast, or not at least as slow, actually just slower, really slower. So that's like saying little o of g of n is the set of functions h of n such that for all c greater than 0, so this is where it's starting to look more like an epsilon delta ball. For all c greater than 0, there exists an n0 such that, I should check this because I think I didn't get this right when I wrote it up. Oh, no, yeah, I didn't need that. Yeah, okay. I don't need another form. There exists, no, I do need. Where did I write little o? Oops. Yeah, in the definition of little o in the course notes, it needs a for all n greater than or equal to n. It's missing this part, so it actually needs 3 quantifiers. H of n is less than or equal to I think this one usually is just less than, but it doesn't matter. C times G of it. Right? So this is sort of like an epsilon delta ball thing. And it's saying that you choose any C you like that's greater than 0, then there is an n0 sufficiently large such that for any value larger than that, h of n is less than that fraction times g of n. So like you say, okay, is there time when Simon's time is going to be 1/100th of Travis's time. And you say, okay, yes, for sufficiently, you can take those n is 3, so saying that n to the 3/2 is in little o of n to the 7/4. This says, okay, is there a time for all sufficiently large values n? Is there a time when this is going to be 100th of this for all values, regardless of constants? Yes, there is. It'll be 1/100th. You say, okay, what about c is equal to 1/1000? Is there a time when Simon's time, is there a distance for which, for any distance larger than that, Simon's time will be 1,000th of Travis's time? Yes, there is. For anything after a certain distance, Simon's time will be less than 1,000th of Travis. 1,000,000th? Is there a distance? No. I mean, Travis is going to be dead by the time he tries to run this distance. But is there a time such that, for any distance longer than this, Simon's time will be 1,000,000th of Travis's time? Yes, there is. Okay, so this is saying, and not surprisingly, you can also just say that you can write this in terms of limits. Okay. And then little omega, as we said, like little omega is just flipping things around. So little omega of g of n is the set. And I went and wrote equals again here. Is the set h of n, and it's the same stuff, such that for all c greater than 0, there exists an n0 such that for all n greater than or equal to n0, h of n is greater than or equal to c. Yeah, I see how you thought it was an e times g of n. Is there, so this is just flipping things around and saying, is there a distance such that for any distance further than that, Travis's time will be at least 1,000 times Simon's time? Yes, there is. Okay, so again, you flip things around. Let me just check to see if there's anything I'm supposed to be saying in here. Yeah, you can do this in limits. There's sort of a set of relations about these things. Oh, one thing that I should say. Oh yeah, so g of n is in big O of g of n. G of n is in big omega of g of n. G of n is obviously in big theta of g of n. G of n is not in little o of itself, and g of n is not in little omega of itself. So I drew a Venn diagram for you, because everyone loves Venn diagrams. Maybe I should just open the new set of markers. Question? Somebody has a question. What in here, h of n is less than or equal to g of n? Okay, the less than or equal, so this is why I don't like people writing the equal sign, because equality is reflexive. So if x equals y, then y equals x. But if n is in big O of n squared, then n squared doesn't have to be in big O of n. It's not. So really just think of this as sets. Just if you want to stay straight, keep things straight, just sort of get used to these definitions. Or you can think of it in terms of limits. F of n is in little o of g of n if limit is f of n, limit as n goes to infinity of f of n over g of n is 0. Is big O that, okay, limit or check the book. So the Venn diagram it's also, all of this is in the lecture notes. The Venn diagram is, the Venn diagram is going to be bigger. No, it's going to be bigger. Slightly bigger. This is in the lecture notes as well, okay? So, this is big O of G of n. This is big omega of G of n. In the middle is theta of G of n. This is little o of G of n. Notice it's a proper subset of big O of G of n. It's proper because it doesn't include this point here is G of n. And then this is little omega of G of n. Okay, so now notice that this isn't everything. Okay, because there can be things which are not big O and are not big omega of G of n. This messes some people up. For example, if you consider the functions yeah, I'm going to put an absolute value sign on these for. That's hard to read because it's near the reflection. Okay. Let's suppose f of n equals n dot absolute value sine n. G of n equals n times absolute value of cosine n. Okay, what are these going to look like? Well, it's going to look sort of like boing, 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 boing. Okay, so that's going to be one of them. And then the other one, and you get stuff like this bouncing up and down. And another of them is going to be sort of boing, 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 boing. Now, because it's sine and cosine, when one of them is bouncing up, the other one is bouncing down. Okay, so is there a time when you can say, oh, the red line is, I mean, notice at this point, the blue line is way bigger than the red line. But at this point, the red line is way higher than the blue line. You can't say that these things are not about, it's not like, ooh, for a sufficiently large n, they're within a constant factor of each other. Doesn't work, they're not theta. And it's not true that the red one is at most about, because they're at most about the blue line, because there are times when the red line is way higher. And it's not true that the opposite of truth, it's not the blue line is at most about the red line, because there are times when the blue line is way higher. For any, you can't, and more than a constant factor higher for any constant you happen to choose. You can't compare these like that. So for equality, you can have, okay, x is either less than y or x is equal to y. If you're talking about numbers, at least real numbers, x is less than y, x is equal to y, or x is greater than y. Okay, it's like, you know, these are the three possibilities. But here it's like, yeah, we just can't compare these. Even for large values, there's still, you know, there are times when one is bigger, there are times when the other is much bigger. Okay. Textbook, Khan Academy, actually, as it says in the lecture notes, one of the, Thomas Corman, who's one of the authors of CLRS, the first author actually, he also wrote he's also a co-author of the, I gave a link to it, of the lesson on asymptotic notation in Khan Academy. Okay, half an hour. So what I want to talk about is people often, in previous classes, people have said, I don't know where they get this, but they say big O is when you're talking about the worst case, and big omega is when you're talking about the best case. And that is not right, okay? It's quite confused. Big O is at most about, and big omega is at least about. And you can say at least about in the worst case or in the best case. You can say in the worst case, we're going to need, you're looking at, think about like how you would talk about like real life stuff. You're going to say, ooh, well, how long is it going to take us to drive from here to here, here to there? Well, in the worst case, you know, if the tire goes flat and, you know, this happens and it starts to rain, it's going to take us at least about a day. Yes, big omega is a lower bound and big O is an upper bound. So this is like big omega is at least about and big O. So you can say it's going to take us at least about a day in the worst case. Maybe on a good day, it'll take us 2 hours. But, you know, on a really, really bad day, it takes at least about this much. That's something somebody could say. On a bad day, it will take at least this much time. You could also say, on a good day, it will take at most this much time. You know? So, I want to give an example. I'm not sure I'm going to get through the master theorem today. But I want to, because I want to do sorting on Wednesday, and then maybe I can teach that. Okay, and we start the little camera again. So lower bounds are really important. So this is the part that I actually get excited about. I know it seems like I'm always excited and speaking quickly, but this normally, like asymptotic notation, it's not that thrilling. It's handy, it's really useful, but it's not sort of my favorite topic. Lower bounds are super cool. So I'm going to give you an example of a problem. This is actually the first problem a bunch of us in my third year, this was a problem we were given in my third year algorithms course when I was a student, and a bunch of us managed to figure out a tight bound for it. And we were super excited because we really felt it should be possible to do better than we were doing. And then we managed to show that no, we actually couldn't, because we were really frustrated. So let's suppose that I give you a matrix. Well, I give you a scratch card, and it has it's a square matrix. 1, 2, 3, 4. Okay. And I tell you that in here are, so it's one of these scratch cards. It's covered in this silvery stuff. So every cell in the matrix contains, so it's n by n. Did I hit the record button? Yes. It's n by n. I tell you that every cell contains a number between 1 and n squared. And every row is sorted and every column is sorted. Okay, and now I have a hat. It has all the numbers between 1 and n squared. You're going to pick a number out, and then you have to either find the number in the matrix by scratching off the cells, or you have to prove to me that it's not there. Not all the numbers have to be there. It just has to, like the numbers that are present in the matrix can be a subset, because some numbers can be repeated and some numbers can be completely absent. 6 by 5, wait, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Okay, oops. Yeah, got that wrong. Okay, so how many cells do you have to scratch off in order to either find the number you want, the number you drew out of the hat? Yes, it's in the notes. So you draw the number out. Well, imagine that you reach into the hat and you pull out a 1. Okay, either it's here or it's not there at all. Okay, so if you're super lucky and you reach into the hat and you pull out a 1, or you pull out an n squared is either here or it's absent, then in the best case you pull out a 1. And in the best case, it takes you at most 1 and at least 1. So in the best case, how many cells do you have to scratch? Theta of 1, right? Actually, exactly 1. Usually we don't worry so much about the best case, but I am going to talk about it in the next class when we do sorting. So what is the worst case? Okay, so now I'm going to show you that even when we're talking about the worst case, we want to talk about at least, right? Because we don't just want to say, I can say, well, it's going to take you at most n squared. And even if I tell you that it's going to take you like at most n log n, at most n, at most n, you don't just care about that. You want to know, yeah, but is my answer really the best you can do? And to say my answer is really about the best I can do, you need to be able to say you need at least about as many, you need to scratch at least about as many cells as I'm scratching. Okay, so can somebody tell me an upper bound for this problem? I need at most, just write it in the chat. I need at most some function of n to be able to find that either find my number or to show something. Yes, I need at most n squared. Somebody wrote n squared. Because if I scratch off everything, then I'm either going to find it or I'm going to be able to prove it's not there. So this problem, there is an upper bound of n squared. Okay? Can anybody give me, can we do better than that? Can we do O of n log n? Can anybody tell me an algorithm? Yeah, you can do it because every row is sorted, right? And every column is sorted as well. So you start and you just do binary search on every row. It's going to take you n log n in each row, and there are n rows, so it's going to be O of n log n. Okay, so actually we have, in the worst case, it's still going to take big omega of 1, because you're definitely going to have to, it's going to take at least 1. You're going to have to scratch something off, because you have to prove to me that, either the numbers, in the worst case, it's still going to take you at least 1. So notice these aren't tight. We have this big gap at the moment. Okay, master theorem is happening on Wednesday. So can anybody see something a bit better? For this interest of time, I'm going to tell you what the tight bound is. So what you can do is, say you're looking for x. I'm so tempted to write that as just r with no apostrophe, but okay. So what you can do is start here and walk along until you get to something that's greater than x. And then, so let's say you're looking for x equals 15. Okay. So let's suppose that, so you walk along until you get to, okay, suppose that here, this is 13, and then you get to 16. And you're like, oh, okay. So now you've found sort of this line, because everything below a certain line has to be bigger than x, greater than or equal to. Well, let's say bigger than x. Everything above the line has to be smaller. And so you're like, oh, well, okay. So maybe this is 12. So this is 3, 5, 6, 10, 12. And then you say, okay, so maybe this is 19. And then you find out like this is, okay, this is 13 again. And then this is 11, this is 20, and this is 18, and this is 12, and 14, and 23. Something like that. And we don't even really care about these because we never need to look at these because the rows and columns are sorted. Oh, yeah, okay. So you don't need to look at these, you just sort of walk down and you trace this line. Okay. So if x is going to be here, it's got to be on the line. Okay, how long does this take you? It takes you, well, walking across and then sort of tracing this line. How long is the line? It's n. So this takes O of n. You can do it in linear time. But now there's something, this problem, so actually maybe this is what somebody meant when they said binary search. It feels like what you can do, you have the matrix and you look at the middle element of the matrix. Okay, so if you're looking for x equals 15 and this is 20, then you know that you don't have to look anywhere here. So you've just wiped out a quarter of the matrix. Okay? On the other hand, if this is 10, then you've wiped out the top left quadrant instead of the bottom right quadrant. Okay, so it feels like you could get something like binary search, but a two-dimensional kind of binary search, right? Does anyone, I could click this button that says poll. I could ask people if they think this sounds plausible. Yes, it totally makes sense. We were convinced, but the problem is it doesn't, like you try and you're like, yeah, okay. So then we know we're up here, and then where do you look? Well, so if you're lucky, you look here, and maybe this is still 17, then you wipe this out. But that doesn't shrink it as much anymore, right? Because this shrank it by a quarter, and this is not a quarter of everything remaining. So, and then because it's like you have to recurse because this part doesn't relate. It's really frustrating because it feels like it should be easy. And then you keep trying it and it's not easy. And then you just feel stupid. And you wonder if it's just you or you need your favorite shoes and a coffee. And you think about it and think about it, and it really bugs you. And then you realize that this is why the lower bound is so nice, because the lower bound, if you think about this argument, it feels like you should be able to do it in polylogarithmic time, like log n or log square n or something. But if you imagine somebody gives you the matrix and these are all ones. These are all fours. And on this line are all threes, maybe. Except maybe they're all threes, or maybe one of them is a 2. And you're looking for, oh, I should have done this with 5, with 15, but let's say you're looking for x equals 2. You have to check the whole diagonal. If you don't check one cell on the diagonal, maybe that's where the 2 is. So these are all sorted, right? Every row is sorted, every column is sorted. And if these are all threes, you have to look at every 3 to know that none of the threes are a 2. So how many cells are there on the diagonal? N. So that's where we get this lower bound that says you have, in the worst case, not in the best case, but in the worst case, you have to check big omega of n. And then we have big O of n and big omega of n. And how many cells do you have to check in the worst case? Theta of n. This is now a tight bound. You can stop kicking yourself about trying to get the binary, two-dimensional binary search to work, because it's not going to. So this is when you get to go. Now, maybe somebody like messes around and gets something that works better on average. Fine. Maybe they're a constant factor better. Maybe instead of walking across, maybe they use binary search to find this red line. Maybe, but still, in the worst case, they're not going to be more than a constant factor faster. So we have a tight bound, n not h. So, and notice that I was talking about the worst case, and I was using big omega. Big omega is a lower bound. So now I have, it's not best case, worst case. It's completely orthogonal to best case and worst case. So now we have this tight bound, and we all get to relax, because now we know that this problem takes a linear number of, you need to probe a linear number of cells in the worst case. And so there's this satisfaction of having a tight bound, that nobody is ever going to get something that's much, much better than we've just got, okay? And we have 12 minutes. I could sort of teach the master theorem in 12 minutes. Yeah, because, you know, master theorem is probably also on Khan Academy. So it's also in the lecture notes. So this way, any questions about this stuff so far? And does anybody want to tell me, where do people get, Okay, so you can also talk about average case. But if you're very unlucky, you would have a matrix like this, you would reach in the hat and you would pull out a 2. So usually we're just going to care about worst case. Although in the next class we are going to talk about expected case of quicksort and quick select. But yeah, you have expected on average, probable high with high probability, all kinds of. But usually people care about worst case. well, theorists care about worst case, and practitioners care about real life. It's very hard to talk about real life theoretically. Okay. 10 minutes for the master theorem. Okay, so now that we know what big O, big omega, and big theta mean, we can actually read the master theorem. So it's in the textbook, which isn't actually our textbook, it's the optional textbook because it's expensive. And I don't use it that much. So but I need to just check what the master theorem says. And I need to fix that thing about the missing quantifier. Oh yeah, and I have also this note about Stirling's formula. About Stirling's formula has a big O in it, and it's saying that's not the worst case. In what sense is it bad? Okay, so I have, yeah, this is long. Okay, so oh, so this is kind of cool. You remember I said that that Appel and Haken, the four-color theorem, Haken got his daughter to check the proof, check a load of cases. I mean, they got the computer to check the actual case, but Dorothea Haken, and then she got married, Dorothea Blostein, and she was my third-year algorithms professor. Her PhD was actually the master theorem. So it was Cedric, I forget who, but there were like three authors, and I think she was the middle one. The constant. Let f of n be a function. And so this is for solving t of n be a recurrence. Defined on the non-negative integers. Such that t of n equals a t n over b plus f of n, where we interpret, okay. Where n over b could be floor n over b or ceiling n over b. Ceiling. Okay. So there are three cases. If f of n equals big O of n to the log base b of a minus epsilon for some positive constant epsilon, then t of n equals theta n, no, yeah, to the log base b of a. If f of n equals theta n to the log base b of a, then t of n equals theta n to the log base b of a log n. I should just mention here that in the textbook, this is LG. I'm writing it in log because it's standard. Once you're inside asymptotic notation, changing the base of the logarithm only changes a constant coefficient, right? Like if you go from log base 10 to log base 2, it just multiplies it by log 2 over 10. Yeah. Log 2 over log 10. Okay, so switching bases, as long as you don't go to something, as long as you don't go to base 1 or base less than 1, which doesn't make any sense, usually, then it doesn't matter, and the constant coefficient is hidden in the asymptotic notation anyway. I just want to say this last part, and then I want to say what the intuition is. If blah, blah, blah equals omega, this is not the strongest version. Last year, I put something about this cannot handle all recurrences, obviously. It just handles a lot of recurrences that come up in divide and conquer. It doesn't handle, for example, the stuff that we saw on colors, on coloring graphs. But this is usually what you get in like third-year algorithms. You get divide and conquers that do this. So Karatsuba, it's in the lecture notes, Karatsuba, Strassen, merge or quicksort, blah, blah. Is omega n to the log base b of a plus epsilon for some positive constant epsilon, then t of n equals, oh yeah, there's a load of other stuff, rats. I'm not going to write all of that. So, and blah, blah, blah. There are a bunch of conditions here. Then t of n equals theta f. So I have about 4 minutes left, 3 minutes left. And I just want to say, you can practice this and see this, but I want to say sort of what the intuition is. Okay, so if you think of your divide and conquer, you're subdividing the problem. At the root, you have the problem. There are notes. There is stuff in chat. Okay, inside asymptotic notation, the base of the logarithm doesn't matter. Okay. And so it's traditional just to write log. It does matter when you're in an exponent. But as long as it's down here in the base, then here it could be log base 2, log base 3, log base 10, it doesn't matter. Natural log, whatever. Because it's in the exponent, it does make a difference because then a constant coefficient in the exponent is important. Okay. If you think of a tree, right? So you start at the root of the tree and with the problem, and you cut it into some number. So this is saying I'm cutting it into like A sub-problems of size about n over b. So I'm cutting it into, and if you cut it into, so remember Strassen, you're cutting something into submatrices of size n over 2 by n over 2, but there are 2 matrices, 4 submatrices, in each of them there are 8 submatrices, but then you're actually doing 7 multiplications. So A and B don't have to be the same. So I'm cutting it into subproblems. And so subproblems with a size about a bth, the size of the original problem, and then I'm cutting into A of them. Okay, so you think of this as a tree where your branching factor is about A. Okay, and the cost of sort of cutting things into subproblems and then you recurse. And so doing the cutting, doing the subdividing, and then later when you get these sub-solutions, you have to glue them back into a solution of the whole problem. That's taking you time f of n. Okay. So now this is saying this is in the lecture notes, right? Oh yeah, so this is the case where you're chopping a lot and the sub-problems are, okay, 1 minute, okay. In this case, the weight is at the leaves, okay? Most of the work in this tree is gonna happen at the leaves because you're subdividing fast enough that the work is down at the bottom because the tree is getting fat. Okay, it's getting, like there are a lot of leaves, the work is down at the leaves. In this case, it turns out that you're subdividing at about the same problem, at about the same speed that the problems are shrinking. In this case, you're doing about the same amount of work at every level. So if you've seen merge sort, right? And merge sort, you're doing linear work on lists which are shrinking, but at each level, if you sum up the total length of the lists, it's n. So the work you're doing at each level of recursion in merge sort is about theta n, right? So you're doing about the same work at each level of this recursion. How many levels are there going to be? It's going to be like log base b of a, and that's why. Okay, so I got something wrong, but you're doing so you get this extra log n factor. Okay. Oh, these are constants, that doesn't matter. Okay. And then the other case, this last case, and then we're done. I'm sorry, I'm over time. This last case is when the subdividing and the joining the subsolutions together, that's really expensive, right? So you're chopping the pieces, but then so for example, if it takes you time 2 to the n to do the subdivision, then and you chop into like 5 parts, then it's so much easier. It's so much easier to deal with the subproblems than to deal with the main problem, that then what dominates is the f of n. So in this case, it's the leaves that are important. In this case, it's sort of every level is equally important. And in this case, it's the root that's important. And I just wanted to say that because that I find people tend not to get if they check other sources about, but you can find out about the master theorem. This is all in the lecture notes anyway. Might have some typos and I might have got some stuff backwards, but like I said, nobody gets this perfect all the time. Okay, sorry, I'm 2.5 minutes over time. Lecture stops. Have a good day. It's a beautiful day outside, at least in the North End. Okay, any questions? You can go, if you have to go to another class or something, you can go. If you want to have lunch, that's fine. If you want to ask questions, I can stop the recording now and you can ask me things. Okay, stopping the recording now. Yes.